Okay, welcome to this week's Non-Creative Geometry and Topology seminar. This week, our speaker is Manish Kumar from IMPAN, and he'll tell us about factoriality and fullness of q-Araki-Woods for Neumann algebras.
Thank you very much. Thank you for the invitation. So I will talk about certain von Neumann algebras, which is probably not the main theme of this seminar, but I will try to make it accessible. So the main outline of the talk is to understand some of the structural properties of this so-called q-Araki-Woods von Neumann algebras. So I will tell you the construction of these von Neumann algebras, and then the main properties that I am interested in are factoriality question and fullness question and non-injectivity question of these von Neumann algebras. And this is joint work with Adam Skarsky, Matthews Wasilewski, and a very recent work with Simon Wang that is also I'm going to talk about. Okay, so let me just start with definition of von Neumann algebra. All of you must be familiar with. So I'll just state the algebraic definition. And they are self-adjoint subalgebras M of bounded operators on some Hilbert space. So for us, the Hilbert space will always be separable and complex. Such that this is equal to its double commutant, where commutant is all elements which commutes with every other element in M. So this is an algebraic formulation, and in analytic formulation, these are precisely those C star algebras which is closed under a strong operator topology or various other weak topology like weak operator topology or sigma weak topology. And M dash here is the commutant of the commutant. Okay, and the von Neumann algebra that we will be considering will mostly be factors. So a factor is a von Neumann algebra. The center is trivial. The center is the element in M which commutes with every element in M. So this is trivial. Okay. And these special von Neumann algebras are in some sense building block of the general von Neumann algebras that you study. So it is enough to understand these enough to understand factors in order to understand general von Neumann algebras. So they are essentially different. There are three types of von Neumann algebras, three types of factors. So you may have seen like I1n. So these are precisely n cross n matrices, complex matrices. So n is here some natural number. I infinity, they are bounded operators on some Hilbert space. So here dimension is infinite. Then so these two are type 1 von Neumann algebras, and type 1 can be divided into two categories. Then there are type 2 von Neumann algebra. So they are infinite dimensional factors equipped with a unique normal trace, normal traceable traceable state. So this particular type excludes n cross n matrices. So they are only infinite dimensional. And then there are two infinity. So the type 2 factors can be divided into two categories. So they can be described like this. So usually you won't see these kind of definition in books, but I am just giving you a general setup. So this is for Neumann algebraic tensor product. And if any factor which does not fall into this category, then we call them type 3. Okay, so which means that this type of the factor will not be finite dimensional, they will always be infinite dimensional, and they will not possess any tracial state in particular. In fact, they don't have any tracial weight. So there is no traciality of any weight or state in these factors. Okay. So the examples that we will be seeing will mostly be of type 3 factors, and the q-Araki-Woods phenomenal algebras that we will construct with particular interest are coming from type 3 factors. Okay, so some example. So the group phenomenal algebra. Let G be a countable and discrete group. And then we consider the left translations, unitaries. So these are the lambda is take the unitary here, and they act say one function like this. So they are translation operators. And the group phoneme algebras are generated by these unitaries. So they are just the weak closure of the reduced group siesta algebras. Okay, so various properties of the group actually get transferred to the group phoneme algebra level. For example, when is this a factor? So G is a factor precisely when G is of ice, G is of infinite conjugacy class. So all non-trivial element of the group will have infinite conjugacy class. And this is a very nice property for phenomenal algebras, which is, I think, in general not true for reduced siesta algebras. Like simplicity of the group reduced group siesta algebra is not so easy to describe in terms of the group. Then in particular, if G is ICC, then they are type 2 one factor. So in this case, we always know its type, and it is of this form, and you can give the tracial state with the unique trace given by this. There delta function on the identity E, and this is the only normal faithful tracial state here. Okay, and the amenability of the group is transferred to the property of the phenomenal. There was something called injectivity, or there are various other equivalent conditions. So I will just write here. Here it is injective. So I will define what injective means. If and only if G is amenable. So the phenomenal algebra that we will be seeing will mostly be non-injective phenomenal algebra, which will actually be non-injective phenomenal algebra. So in particular, if it comes from a group, then it has to be a non-amenable group. What do we mean by injective von Neumann algebra? So here is the definition. So any von Neumann algebra, say if it is represented on a Hilbert space, this is called injective. If there is a projection, so injective, you can think it as an operator system or as an operator space. So injective, if there exists a projection of non-one. So projection simply just means that, or idempotent, that it's a square G and it's normal. Okay, so this particular definition is they are equivalent to many other very equivalent conditions for von Neumann algebra. Like there are notions of amenability of Banach space. So for von Neumann algebra, amenability actually is equivalent to injectivity. Then there are notions like hyperfiniteness or approximately finite dimensional von Neumann algebras, which means that you can approximate it by finite dimensional subalgebras. Then there are various other notions that was classified by Alan Kohns. And these notions are not so, so there are not many equivalent notions in C-star algebra category, C-star algebra world. But for Neumann algebra, things are very nice here. So in particular, examples of injective von Neumann algebras are group von Neumann algebras, whenever the group is amenable. And so examples of injective factors. So any finite dimensional von Neumann algebra or VH, then LG if G is amenable. So this is an example of type 1 injective factor, type 2 injective factor. Then type 3 injective factor is like, I'm not going to describe what they are, but I think they're called infinite tensor. So these were so I'm not going to explain what they are, but they were introduced in late 60s by Araki and Woods. They are some kind of tensors, infinite tensors of finite dimensional von Neumann algebras. And examples of non-injective factors. For example, LFN. So Fn is a free group. So this is again because this is not amenable, so the group von Neumann algebra will not be injective. Then the example that we will be interested in, V or Q Gaussian factors. So these two examples is the theme of this talk. So I will give the construction of these factors, and they are particular examples of these q-Araki-Woods factors. Okay. So now let's go to the construction of q-Araki-Woods. So to begin with, there are three data that you start with, and out of those three data, one constructs these polynomial algebras. So what are those parameters? So there is a number associated to this polynomial algebra. So some number strictly between -1 and 1. Then there is a real Hilbert space. So we will remain in separable case. So separable. And on this real Hilbert space, there will be a representation of a real number onto the orthogonal operators on the real Hilbert space. So this is one parameter strongly continuous group of orthogonal operators. So out of these three parameters, we will construct certain Fock spaces. And if you have seen the construction of Fock spaces, then there are some natural operators like creation and annihilation operators. And out of those creation and annihilation operators, we will define these fundamental algebras. Okay, so here goes the construction. So what we do is, even if we are starting with a real Hilbert space, we will ultimately consider complex Hilbert space only. So first we complexify the real part. So we will see why we are starting with a real Hilbert space and then taking its complexification. So consider its complexification, and then you naturally extend these operators to a unitary operator. So these are the natural extension to one parameter group of unitaries. On this complexification. So for these one parameter group, we can use Stone's theorem to write it as an exponential of certain operator. So ut tilde can be written as like this, or e to the power ith if you prefer, where it is positive self-adjoint, possibly unbounded. So I said unbounded densely defined positive self-adjoint invertible operator. So invertible in the sense of unbounded. So it means that it has zero kernel and dense range, so that you can define the inverse as a densely defined unbounded operator. Invertible operator on H. Now we use this A to give or to define a new inner product on the complex Hilbert space. So what we do is define a new. So these two data are actually used to deform the original inner product. And this is the first deformation that we are doing from the first data. So define a new inner product on HC by. So we are denoting it by the subscript U. And this inner product is in the original sense. So you take two vectors from the complex Hilbert space, and okay, so the definition may look not so natural in the beginning, but this definition somewhat is related to the original idea of Araki-Woods. So this is U. This gives proper inner product on this Hilbert's on this space HC, because this is an invertible operator. A inverse is a positive operator, so 1 plus A inverse is a bonded positive operator, bonded invertible operator. So this is a well-defined inner product, and now we consider its completion. So the completion with respect to this new inner product on the norm. So with respect to this, the norm coming from this new inner product, we take its completion. So this is the first deformation that we have done using this data. Now we will do. Sorry.
Is it ever the case that it coincides?
Only when A is identity. So only when UT is trivial. And we will see that it never coincides when U is non-trivial. So this is 1 plus A inverse, and then we again take its inverse, the whole. Yeah. Okay. So this deformation is due to Selektenko. Now I will describe the second deformation using this number, and that is due to Bojai-Spiker. So now we consider the Fock space construction. So consider the free Fock space. So Q has not played any role yet. It will come in this construction. So free Fock space is just the direct sum of the tensors of these Hilbert spaces. And the zero, so they are called particle spaces, nth particle spaces. So zeroth space is just complex number, and you always fix some unit vector. This is called vacuum vector. So what we do is we define a new inner product on this space using the parameter Q. That will be the second deformation that we'll be doing. So the original inner product on this Fock space will correspond to the case when Q equal to 0. So for Q non-zero, things are changing. Similarly, this original inner product that we have considered there, that will be precisely the original. So this new inner product will precisely be the original inner product when U is trivial. So when U is trivial and Q is 0, then you are not doing anything new. It will remain the. Okay. So on the algebraic tensor product, define the operator. This is a notation using PQN. It depends on Q and N. So on simple tensors, we define this operator, and then you extend it linearly, and it has to be checked that it is well-defined extension. So on simple tensors, it is defined like this. So you sum it over permutations of n symbols, And here Q is coming into the picture. So these are just summation where we are permuting the vectors and summing it over Q to the power something where this is the number of inversions of the permutation. So if you have seen symmetric Fock space or anti-symmetric Fock space, then if you take Q equal to 1, then this just goes away. And this summation is nothing but symmetrization of any tensors. Similarly, if you take Q minus 1, then it is anti-symmetrization, if you say. And we are like in between symmetrization and anti-symmetrization. So Q is precisely in between GM. And then you extend it linearly to the algebraic tensor product. And Bojeko spikers. They showed that this defines, I think this is from 91, a strictly positive linear operator. So for this definition, you can do it with any Hilbert space. It doesn't have to be with HU. It can be with any Hilbert space, but I am doing it for HU because we will be in that world. So this defines a strictly positive operator, meaning that if you consider these one, then this gives you a genuine inner product. So if you consider this new form given by this operator, then it gives you a genuine inner product. But
Definition of positive.
so positive in the sense that, yeah, this is a non-negative number if you take the same vector. And a strict positivity means that if it is 0, then the vector has to be 0. But this strictness is not true in general when you take Q equal to 1 or minus 1. So in symmetrization or anti-symmetrization, you have to quotient it by vectors which is whose inner product is 0. But for Q strictly between minus 1 and 1 and minus 1 and 1, this already turns out to be a strict positive. So this is a factor proved way back in 91. So this gives an inner product. Yeah. So positive simply means that this is positive. So that it defines a positive definite. A strictness means that it gives you an inner product. Like it's not semi-inner product, but it's a genuine inner product. So that's what a strictness. So yeah, I mean the meaning of this sentence is this, that it is an inner product. Okay, so now we have done second deformation, and as before we take completion, and for this notation I am using here, Q is coming into the picture. with respect to this Neumann. Okay, and then as before, we take their direction. So this is a different Hilbert space than the Fock space. Okay, and for n equal to 0, this is just C, and we keep a fixed vector there also. So if you take q equal to 0, then you get back to the original free Fock space there. But for q non-zero, you are getting a different inner product. Okay, so now we have used all the three data. So we have got the Hilbert space on which our von Neumann algebra will be acting. So we define some operators on this Hilbert space, and von Neumann algebra will be generated by them. So these are called Q creation operator. So on free Fock space, you may have seen the creation operators. So the definition here is exactly that. So if it's for any vector in a Hilbert space, we define this left creation. So this is Q left Q creation. So this is an operator. Okay, so we first define we give the definition of this operator on some dense subspace, and then I will just say that it extends in a very natural way. So on omega, on this fixed vector, it sends omega to the vector psi. So this vector is now in H1. Okay, and if you consider any n tensors, then what you do is you just attach psi to the beginning of this. So n tensors are sent to n plus 1 tensors. So this definition is only at the algebraic level, that you extend it linearly, and then it's a matter of some calculation that it actually defines a bounded operator. So it extends to a bounded operator on the whole space. For q equal to 0, boundedness is easy to show, but for q non-zero, it's a bit work. So I will just write it here again. This is delta normal constant that extends low bounded linear operator on this Fock space. Okay, so in this construction, the role of U is not there, even if we are considering HU as such, like properties of boundedness and things like that is not being interfered from the one parameter group that we are considering. This is purely the fact based on Q and how we are defining the product. And you can explicitly give the formula for the adjoint. So this is called left annihilation operator. So if you suspect that here zero particle space is sent to one particle space, but here the annihilation will send n particle space to n minus one particle space. So 0th space is sent to 0, and n tensors will be sent to n minus one tensor. So this is given like this. So you remove the kth vector and you can highlight it like using inner product of by side, and then you sum it over. So for q equal to 0, you will see that this summation is just one value. Like for q equal to 0, we will take 0 to the power 0 equal to 1 in that sense. So this will, what this formula will do is just kill the first vector, and other vectors are the same. Okay, so this will again, this is the adjoint of this creation operator. So they are called an annihilation operator and definition. So the von Neumann algebra will be generated by sum of these operators. So this is this definition as you go through here. Q generated by or defined by. So here is the notation. So it is depending on 3 parameters. So it is generated by the sum of the creation and annihilation operators. This acts on this box space. And this is where we are using the real part. So the vector is varying only over the real Hilbert space. And so far, the real part has not played any role. Whatever construction we did, we could have done for any complex Hilbert space. But to define this von Neumann algebra, we vary this vector only over the real part. If we were varying it over arbitrary psi, then actually this von Neumann algebra turns out to be equal to the whole boundary operators. So that is not an interesting, not so interesting von Neumann algebra for us. Okay.
Can I ask?
Yeah.
Okay. A couple. It's just I'm a little caught off guard. I was a bit unexpected that this is the way that the Q deformation was going to go. In the sense that you deform the actual inner product of the Hilbert space. Like so naively, I might have been thinking, okay, you start with this notion of a creation operator, and then you Q deform this action. So you leave the inner product on the Hilbert space alone, but then sort of deform this operator in a Q way, maybe by a similar formula, indeed. Do you see what I mean? So you deform the algebra as opposed to the space on which the algebra lives, is what I was expecting.
Yeah, so I okay, so maybe what you're saying that you define the two operators,
yeah,
like this,
yeah,
and then get the inner product using in a sense that these two has to be adjoint to each other.
yeah.
In that sense,
I mean,
so you can.
Yeah, so I would have left the inner product alone, and then I would have started off with this naive definition, and then I would have Q deformed this action, maybe by this formula that somehow, and then the adjoint would just be its adjoint, whatever. Yeah. So yeah,
Yeah, so it will be the same kind
it
of
would get
argument.
but I just wonder whether you would give indeed the same.
Yes, so I
Yes,
think
yeah.
in the original paper it is done that way. That,
Okay, I see.
like they define two different operators.
Yeah.
And they say that there exists an inner product in which these two operators are adjoint to each other.
Oh,
So they say it like that.
I see. And
Yes, so their idea was to say that, okay, so what they were answering the question of that, okay, there are some operators which satisfy some kind of Q commutation relation.
right.
And okay, so they defined the operators in this way, and they said that there is a Fock space representation of such operators.
Okay.
And they then explicitly gave the inner product and the Fock
Okay.
space in that.
I see. And then, but then, the other deformation, this with this U, I didn't see coming at all. I mean,
Yes.
so this is completely mysterious to me.
Yes, so I will say why,
Okay, right.
where it will play the role. So far, so the role of U will be coming to change the types of the von Neumann algebra.
Oh, right, okay.
So that
right.
is where the
Thanks.
yes. So how much time? Okay, so now that we have seen the construction, I would like to discuss some of the properties of this von Neumann algebra. So the basic question is that whether this is a factor, whether its center is trivial, and there is no reason why you expect that its center is trivial, but here is the region that you expect. So I will just mention some of the historical background of this construction. So Q equal to 0 and UT trivial case. So when there is no deformation, you just start with a real Hilbert space and you do the construction, things will look very simple in that case. So that particular case was constructed by Voiculescu way back. So this case was the beginning of free probability in some sense. And this case, so in this case, you just have one data, just a real Hilbert space. There is no Q and there is no UT. And he proves that this is actually isomorphic to the free group factor. So it is the real dimension of the Hilbert space. And in this case, it turns out to be isomorphic to the free group factor. Now we know that this is a factor. So this is a factor. So then you like naively you expect that in general things will be factor for general von Neumann algebras. Okay, so in particular, I will just write here. This is a one non-injective. So this is because this is a non-abelian group. This is a non-injective two-one factor. Okay, and this is full. So I will come to this notion of fullness a bit later. Okay. So what happens when Q equal to 0, non-zero and U 0? So this case was considered by Bojaiko. Thank you. So where they constructed all these inner product and all this construction was given in the case when UT was trivial, but I have given you construction when for general UT. So this particular case also you ask whether these von Neumann algebras are factor or not, and in this case also it was shown to be. So now we have one parameter Q and a real Hilbert space, but we don't know if this is a group von Neumann algebra now. That's an actually open question. But what we know is that it is a non-injective to one factor. This is known. This is work of many people. So Bojaiko, Spiker, Snady. So Bojaiko, Spiker proved it for infinite dimensional Hilbert space. So when dimension is infinite, then they proved it to a factor. Snady proved for finite dimensional, but not all of them. But for large dimension, Snady proved, and Ricard actually proved for all the cases. Okay. The third case is Q0 but UT non-trivial. This particular case was introduced by Silakchenko. Yeah. So in these two cases, both the factors are 2-1 factor. But here comes the twist that when UT is non-trivial, it is not a 2-1 factor anymore. But it is still a factor. So This is a non-injective three. Okay, so I should have said it earlier that okay, so before I explain this, I will just say here that the state. So you consider this vector state coming from the vacuum vector omega. This is this is non-trivial if and only if ut is trivial. Ut is non-trivial. This state is non-trivial precisely when your representation is non-trivial. So this representation is introduced to make this state non-trivial. And the moment you go into non-trivial state, it turns out that there is no other trivial state at all, which means that this von Neumann algebra is actually a type 3 factor, that there is no trivial state. This is not obvious, of course, there is a lot of work in between, but it's a fact. And the general question is for Q non-zero, ut non-trivial, whether we can say that it is a non-injective factor or not. So in these three cases, whatever properties we see, we expect them to be true even for general case. And various people tried this. So Q not zero case seems to be a bit difficult case than Q equal to zero case. Even for trivial case, you see three people have contributed in different times their factoriality argument. So here also there are various people using and various people have tried to prove factoriality in different particular cases. So I will just mention some name. Here, some people who have worked in this. Nelson, I think it is in. Um, Adam and Seeming, then these are some of the work I am mentioning here. And I'm not going to tell you precisely what are their particular results, but I will just mention this recent paper. This is from 2022. They actually proved factoriality. So these people proved factoriality when dimension is greater or equal to 3. And for dimension 2, they could not prove factoriality for all the cases, but for some cases they could. Q is away from you. So they could prove factoriality of these von Neumann algebras in this case only when Q is only for certain Q, not for non Q. And I'm not going to tell you what away means here, but it depends on certain other parameters in the dimension of the dimension. So, but in these cases, it was proved for whatever Q or for whatever UT you take. Okay. So this is a factor proved in these cases. And I should just say that they considered mostly the question of factoriality. They did not consider the question of non-injectivity. Non-injectivity was considered by HI in some particular case. But again, these people did not worry much about that. So I will just write our theorem. So the remaining case here was completed by us. So I will just mention. And our result actually works for any finite dimensional case. But and our methods were different than these authors. So I will just write the general case that we proved. And this is from last year. So and if the dimension is finite, then we prove that this polynomial algebra is a type 3 factor. Again, most of these papers also did not talk about type of the polynomial algebra. They only talked about factoriality question. But we also calculated its type. So type 3 is further divided in various types. It's like type 3 lambda, where lambda is in between 0 and 1. So we actually calculated the actual type from the type 3 one. And that depends on the representation that you're considering. Eigenvalues of the representation. So I'm not going to the detail of that. And we also prove that this is non-injective. So the methods that we used gives non-injectivity simultaneously. So non-injectivity, so factoriality question is again solved using the other results for all the cases. And type 3 is also solved for all the cases. I have mentioned it just for finite dimension, but it is now known for all the cases. And non-injectivity is also now known for all the cases. Here I am mentioning just for finite dimension, but using one result of AI and this result itself, you can conclude non-injectivity in all the cases. So I am just writing it as corollary. I am not, again, this is non-injective. For even infinite dimensional case. I should write for all the cases. But this is, okay, there are some arguments involved here from how to go from here to here. Okay, so I will, in few minutes, I will mention the third question that we have been looking into. And so in a minute, if I have to explain what we did here was we considered some kind of something called conjugate variables. And there are some tools from free probability. So even if Q is non-zero, in the case when Q is non-zero, tools of free probability is very difficult to use because there is no freeness. But still, there are some operators which behave even for Q non-zero, which behave in a very nice way as you see in free probability. So that is those are something called conjugate variables, and you use some then free probability tools to and some abstract result from free probability to conclude factoriality, non-injectivity in general for polynomial algebras. So in particular here, that's what we use. But other papers have not used that free probability technique or conjugate variables technique before. Okay, so the final question that I want to mention is the fullness question. So here's the definition on Neumann algebra. Is full. So factor means that the center is trivial. So any element which commutes with every other element from the fundamental algebra has to be scalar. And fullness is some kind of limiting triviality. So if any net if for any net satisfies there's some weak topologies, there's strong operator topology. So if any net commutes in the limit, that's what this means, then it is scalar in the limit. Then there exists any bounded net. Then there exists a bounded net in the scalar. This was to achieve. So this is some kind of, I should say, weaker version of factoriality, that if any net commutes in the limit, then it is scalar in the limit. That's what it means. And if you're familiar with ultra product, then this precisely means that the relative commutant of M in the ultra product of, say, any free ultra filters is trivial. That's what it. So nets you can think as an element of the ultra product, and if it commutes with M, it has to be trivial. That's all. Okay. So I have written here somewhere that these free group factors are full, and you expect the same for these fundamental algebras as well, for Q non-zero, for UT non-trivial. And it turns out that that is true. So in these cases, for trivial case, so for this particular case, fullness is known simply because this group fundamental algebra is full. That is the original result of von Neumann and Murray. They used this fact that they are full, they call it property gamma, and that they said that this does not have property gamma, and use it to say that they are not isomorphic to the hyperfinite 2-1 factors. That's what their idea was. Then later, this notion of fullness was considered by Kohns. And in these cases, fullness is also known by other people. For example, Snehadi in his paper proved fullness of these fundamental again for large dimension of the Hilbert space. In this paper by Selyatenko, he proved fullness, not just non-injectivity. So fullness always implies non-injectivity. That's a fact. So in this case, Selyatenko proves fullness as well. So this particular case is again unknown. This was known only one particular case from Nelson says that it is there full, and then there are some other work by Hudiar and Isono who proves fullness in some particular cases. So I'm not going into the details of what are the things known, but I'll just write here known result. This is, so this is Q non-zero and UT non-trivial. This was known to be full in the following cases. Full when UT is weakly mixing. So when UT is non-trivial, then things becomes a bit tricky. So weakly mixing, if you have seen this notion, this means that there is no finite dimensional subrepresentation. One of the formulation is that no finite dimensional subrepresentation. That's what weakly mixing means. So this case was, so again, why this UT non-trivial case is so difficult to handle is that you have to consider different cases. Weakly mixing case has to be considered separately. Then the part where the part which is generated by finite dimensional subrepresentations, that is called almost periodic. So that case has to be handled separately, and things become very different in those two cases. So this part is usually easier to handle. Again, in some cases it can be difficult to handle, but for fullness, this was easier to handle. So in this case, this was proved. And UT is almost periodic. Dimension is fine, infinite. And A is 1. And this particular case, almost periodic means that the Hilbert space is generated by finite dimensional sub-invariant subspaces. So you can think that Hilbert space is generated by eigenvectors. So this is the part which does not have any weakly mixing part. You can think it like that. So when it is almost periodic, when dimension is infinite, and when A is bounded. So A, if you remember, was that we used A to write the representation like this. So this was the generator of the representation. So A can be a bounded operator. So when A is bounded, then you can relatively, it is easier to prove that, well, not easier, but you can follow somewhat the same argument as Sneady and prove that this is full. So in this case, this is known to be full. This is ODI and Isono. And I will just mention the other cases that we have considered. So here is the theorem. This is with Adam and Matthews. So this is from the same paper. And dimension is finite. Then we could say that this is full. Okay, so I mentioned earlier that fullness always implies non-injectivity, but I have written non-injective argument separately because we did not first prove fullness and then we concluded non-injectivity. We rather somewhat went in the other direction. We first proved non-injectivity and used some other results to conclude fullness. So that's why this theorem is somewhat a consequence of that theorem plus some more argument. Okay. And then there is one remaining case from here. So UT is almost periodic, dimension is infinite, but A is unbounded. This case was remaining. And this is a very recent work with Siming. This is on archive now. UT almost periodic. Dimension A is unbounded. And then this is full. So now the question of fullness is complete in this. So these were some of the basic questions that one asked. Then there are various other open questions in for these phenomena. So we want to study various other structural properties that pre-group factors has, and we want to say that whether these general phenomena algebras have or not. So for example, various other properties for these phenomena algebra when q equal to 0, various other properties are known, or in this particular case also various other properties are known, because here you can use, so this is a 2-1 factor, so we have a traceable state. So there various things become easier to handle. And in this case, various free probability tools are available for q equal to 0 case. So there also you can use some abstract results to conclude various things. But for q non-zero and ut non-trivial, things are a bit difficult to handle. For example, there are questions of whether these fundamental algebras have Cartan subalgebras. So in CST algebra, you may have seen Cartan subalgebras like Massa's whose normalizer is like spanning or generating the whole CST algebra. So here also there are notions of Cartan subalgebra, and free group factors don't have any Cartan subalgebra. So you ask whether the other fundamental algebras have Cartan subalgebras or not. And in these three cases, it is known, but in general case, Q non-zero and UT non-trivial, this is not known. So that is one question that is very interesting to ask, and I have planned to work on that. Then there are questions of very famous question of isomorphism problem. So the question of isomorphism problem of free group factors is well, it's like some very old question which is still unsolved. So there, what you do is you ask whether if n changes, then whether they are isomorphic or not. But now you can ask a different question here, that you keep n, but you change q, whether they remain isomorphic. So I am saying that this is isomorphic to so keeping these two data same, you just change q. Can you say they are isomorphic? The free group factor question asks that q is 0, but you are changing the Hilbert space. Ut is trivial, but you are changing the dimension of the Hilbert space. But now what we are asking here is that you keep the Hilbert space and representation same. Even for a moment, we take Ut to be trivial and just ask this question. Changing q, this turns out to be a very difficult question. I think there are just two papers which proved that they are isomorphic for when q is very close to 0. And the closeness, and when the dimension is finite. So that closeness is depending on the dimension. How when you take large dimension but still finite, then you can expand your value of q in which it is isomorphic. Things like that. So, but general, we don't know anything. For infinite dimension, what is known that they are not isomorphic to the 0 case. So this is known, not isomorphic to T0 if q is non-zero and dimension is finite. So sometimes isomorphism happens, sometimes it does not. And we expect that at least in finite dimension case, this isomorphism is true, but we have no idea how to handle this. Okay, and then I will just say various question you can ask for the underlying CST algebra. So we have considered only for Neumann algebras generated by these creation plus annihilation operators. We can also consider just the non-closure of that. And then many questions you can ask that whether it has Cartan subalgebras. So what is true is that q equal to 0 in UT trivial case, the CST algebra is isomorphic to the reduced CST algebra of free groups. So in those cases, you know various properties. And then you can ask for general case, some of those properties are true or not. And this isomorphism problem is still a well-known problem there also. Like whether all of them are reduced CST algebra of free groups or not. Again, for infinite case, it is known that the CST algebras are also not isomorphic. So then we know that the CST algebra will not be nuclear because the fundamental algebra is not injective, but it is exact because it is contained in a nuclear CST algebra. That's a fact. So exactness is known. Simplicity is not known for those CST algebras. So that is another question that one can ask. So for underlying CST algebra, I think not much has been done. So that is one area that one can look into. Now I'll stop.
Right. Thanks very much for the nice talk. Do we have any questions?
How about traces on the CS algebra case?
So when UT is trivial, then of course we have a
Exactly
trace.
the same as the phenomenon.
Yeah, so the
Right.
trace is traceless state is the same. Whether it is the unique trace for Q non-zero, I think it is not known.
Mhm.
But there is a trace. For UT non-trivial, I think you expect that there is no traceless state. Non-trivial.
This state you've defined.
This is a KMS state, yes, even at the level of C star algebra. So at the level of von Neumann algebra, this is a KMS state because you have this Tomita-Takasaki theory. So for C star algebra, also I think it is known that there is a particular temperature at which this is a KMS state. And I think that I'm not sure how much it depends on the representation, but there is a very explicit construction in terms of the representation UT. Yeah.
And also the way that you define the CS algebra is somehow similar to Kuhn-Simpson algebra. For example, now if
No, so it is contained in Kuhn-Simpson algebra. So Kuhn-Simpson algebra will be the one generated by only the creation operator.
Yes,
But here we are considering a very small small number of operators.
yes, because
it
you
is-
consider the sum of them.
It is some of that.
Oh,
yes.
yeah, okay.
So, but yes, it is contained in Kuhn-Simpson algebra, and it is true there at that level that even for Q non-zero, it is isomorphic to the Kuhn-Simpson algebra for Q equal to 0 case. So that's a fact. So nuclearity comes from there.
Oh.
The exactness of this.
Exactness. Okay, thank you.
Yeah, so I did not write it, but it was something like this. So you take two vectors. And you consider then this turns out to be this. So for example, if you take these to be orthogonal elements, then this commutation relation is 0. This is identity. It does not depend on UT. It's just on. So okay, this inner product you take in U only. So the orthonormal set you have to take is in the new Hilbert space, and then you get a bunch of operators which satisfy this K commutation relation.
So you mentioned,
that you can do this for the C-star algebras, and then you get the reduced group C-star algebra, the
Yes.
free groups or whatever, and similar elsewhere. But can you also consider like a full C-star algebra? And is
Yeah.
there,
So
is there, times when the full and the
I
reduced coincide?
think not, because this is a very particular representation that we're considering. And I think it does not satisfy any kind of universal property here. So you probably don't expect here, but you may expect some kind of universality for the Kuhn-Simpson algebra, for example, that you consider just the one generated by the creation operator.
So you can't define like some sort of, if via these Q commutation relation type things, universal C-star algebra, or something like that.
Essentially what I was asking.
Yeah, I get it.
Yes,
yeah,
yes. So
yeah.
I think I have not come across any paper which considers in that way, and we can say that okay, you consider the universal C star algebra satisfying this Q commutation relation. But if you consider the universal C star algebra satisfying this, then you get the Kuhn-Simpson algebra. You don't get the you don't get this Gaussian C star algebra. But because here the von Neumann algebra will generated by just this creation operators.
But I mean, if you restrict it to the right ones.
But there, so there is no well-known relation between the Gaussian operators. So, for example, if you consider these operators, then there is no nice relation between these kind of operators, and so I don't know what kind of universality, like what kind of relations you want to put to make sure that it satisfies it. I mean, there are relations, but I think there is no well-defined. Like not all of them satisfy in a very nice structured way. So that's a problem.
I have lots more questions about the season though.
Yeah.
So there's nothing else. Let's thank Manish again.
Thank you.
So next week speaker will be some guy